system. That one?
Yes, that's the one.
There we go. It's all yours.
Okay, well, thank you all for coming. I'm going to talk tonight very briefly about some of the lost planets that I think, or lost worlds that I think used to exist in our solar system, but which we don't see anymore. I can see this is going to be one of these. Oh, there we go. So you're all used to the solar system at the present day. It looks quite orderly. You know, you've got a few terrestrial planets here, rocky planets, and then we get out to the gas giants and then the ice giants, and then we question whether Pluto is a planet or not. So, you know, we're kind of used to thinking that this is the way it always was. There always were this number of planets and no more than that. However, the much earlier solar system was a much more messier place. I seem to be having the same problem that Pete was having. A much messier place. So you can see that there's a big planet forming out here, a gas giant, probably Jupiter. And then there are some other planets or planetesimal small bodies here which keep colliding with each other. And then there's a few comets here, and then there's a sun starting to form in the middle and starting to blow away the gas from the solar nebula. And even if you look in scientific journals and articles, you'll see that the growth of planets is often portrayed as a very orderly sort of thing. So we have little ones, which we call planetesimals, and they can be 10 to 100 kilometres in diameter, and they meet with each other. You notice there's no suggestion of big collisions or anything. They just look gently meet, so they become bigger, and we call these things embryos, planetary embryos. They're up to 1,000 kilometres in diameter, and then, you know, all very gently, all goes, oh, suddenly we've got a planet. Okay, so it looks like it's a nice orderly process, but in fact we suspect it's nowhere near that nice and orderly. This is an observation of a planet-forming region around a star. Okay, so this is a real image of a real star and its planet-forming region. This has been taken by a telescope in this area of space. When we saw this, we were amazed because it looks remarkably like computer models of planets forming, but we have made these computer models, we scientists in general have made computer models in which you start with a disk, a flat disk, like an old gramophone record, for those of you who might remember that. And slowly the disk starts to accrete larger and larger bodies. You'll notice that the size of material in... This is very interesting. The size of the material gets bigger and bigger, and then you get these areas where a single planet is clearing out effectively a circle or an ellipse. And that's exactly what we saw in the space, the previous diagram where we see planets being formed around another star. Okay, so we know, however, that earlier in the solar system it wasn't a quiet, easygoing place. There were lots and lots of collisions between planetary bodies. And we know this because of several things. We can first of all do modelling of planetary systems, and this work has been published some years ago now. But what these people do with a computer model is that they're growing Jupiter somewhere out here. This is the present-day location of the asteroid belt. These purple symbols are planetary embryos, and the other coloured symbols are planetesimals, essentially, some of which started in this region, those are the black ones, some of which started in roughly this region, they're the red ones, and the green ones started out here. And you'll see that they've all got mixed up, although there is still quite a lot of inner solar system planetesimals out here, and rather more of the green ones, the outer part of the inner solar system out here. You can still say that, oh look, there's some green ones getting into here, there's a red one there, there's a black one coming up this way, and so on. And this diagram shows essentially the the distance from the Sun, so the Earth is at 1 astronomical unit, and on the other axis it tells you about a thing called the eccentricity of the orbit. And all that means is that if you've got an orbit down, an eccentricity down here, your orbit is more or less circular, and as you go up to values much higher, your orbit is getting to be extremely elongated and ellipsoid. So it's an untidy place with bits of material moving backwards and forwards due to the influence of the growing Jupiter. However, this is not the last of the computer simulations that has shown this. So a later simulation has shown that one of the peculiar things that happened in the solar system, or appears to have happened in the solar system, really doesn't like this, does it? Doesn't like this diagram. One of the peculiar, I'm going to go through it quickly. One of the peculiar things that happened in the solar system is thought to be that Jupiter and Saturn were formed at much, well, in terms of Jupiter was formed at about the point where we find it now, Saturn, and as they grew, and actually Uranus and Neptune, as they grew, they migrated inwards. So this again is an astronomical unit, so Earth at 1. The planets, the large giant planets migrated inwards, caused all sorts of chaos in the inner solar system, migrated outwards again, leaving a very chaotic and messy area in the inner solar system. And at this point you have that moment where the scientist writing on the board says, and a miracle happens, because very much later we end up with a nice, organised solar system again. And here we have the outer planets that have grown, and the Uranus and Neptune have moved out into the outer solar system. So this is called a model called the Grand Tack model, because it has the planets coming in and moving out again. Again, it's only a computer model, but it does explain a lot of the information that we know about the inner solar system, about the solar system in general. Now, evidence even from the planets themselves show us that things were very messy. This diagram tries to show the ecliptic plane, which is like the gramophone record, that goes around the Sun and passes through the Earth. It's the plane that the Earth draws out in the solar system, extended in a long direction. See if we come back. Okay, and all of the planets are actually not in the same plane, which suggests that they have got a problem, or there has been some reason why they have moved out of the plane, the original plane of the solar system. You can't put a single line, a single plane through all of the planets. So it's clear that the planets, instead of very beautifully producing a set of planets in the same plane, some of them are above the plane, like Jupiter. Well, in fact, most of them are above the plane, or perhaps the plane is wrong, the Earth is below. But Pluto here, 17 degrees below the plane, which again casts some doubt as to whether Pluto is really a planet. The next diagram also tells us about impacts and things that have, almost certainly impacts that have occurred, collisions that have occurred before these, as the planets were growing. Mercury, surprisingly, hasn't got much of a tilt of its axis, and neither does Jupiter. Their north pole is at 90 degrees to the plane of the ecliptic, essentially. But the Earth, as you know, tilts by 23 degrees, as does Mars a little bit more. Actually, so does Neptune, and comes to the eclipse, Saturn is a bit on its edge too. So why should some planets have their north-south poles like that and others like this? Possibly because of impact while the planet was growing. There are two planets that have really got themselves into a twist. Uranus here is on its side. Okay, so it's orbiting, it's rotating on its side. And Venus, although it looks superficially as if it's a pretty happy planet, is rotating backwards. So, if you were condensing and accreting your planets out of a single nice planar primitive nebula around the Sun, you would expect them all to be orbiting in the same direction, in the same plane, and also with their axial tilts more or less perpendicular to the ecliptic. Doesn't work. So clearly what has actually happened is that when we have a meeting of two planetesimals or two planetary embryos, the meeting is somewhat more energetic, and we end up with only very, very small fragments of the planets or the planetesimals and embryos that we started off with. Coming back to Peter's talk, we saw the lowlands on the northern hemisphere of Mars. There is a suggestion that those were also formed in some way by collision. And obviously, when you look at the Moon, as we are probably going to do in Louise's talk, you will see huge craters on the Moon. So there's plenty of evidence all around the solar system that we have things bashing into each other, and in those cases, the impactor was probably completely destroyed. There's even a suggestion of the Earth-Moon system, a very strong suggestion that the Earth-Moon system is formed like that. Okay, so if we go into look at our meteorite collections, I'm beginning to see a pattern emerge here. Let's try putting that down. Okay, it's a good idea. Okay, so if we go into our meteorite collections, what we find is that, going back a bit, the bits of meteorite that we assume formed the inner part of the planets, the core of the planets, we've got plenty of those. They are tough iron nickel meteorites, and they tend not to break up. They're very strong. And similarly, the basaltic crust on the surface of a small planet also manages to survive quite well, because all the minerals are interlocking, the crystals are interlocking, and they're pretty tough material. And so we often have pieces of basalt material in our meteorite collection, along with the pieces of core material in our meteorite collection. Unfortunately, we don't have an awful lot of ones that look like the mantle. This is a piece of Earth's mantle, and that's because when you look at one of these in hand specimen, an Earth mantle rock, they tend to fall apart in your fingers, and that's exactly what happens presumably in space when the mantle of a planet or planetesimal is exposed in space. These aggregates disintegrate and we lose them. Okay, so what we see are ungrouped basaltic meteorites and ungrouped metal iron meteorites, and there's about 100 of the iron meteorites and 70 of the ungrouped stony meteorites in our database, for which we have no planet and not even a suggestion of an asteroid from which they might have come. So this material is the evidence that there were lost planets. Okay, so let's go back and check. This is the evidence of lost planets. We cannot say that these come from any planet that we know, and we can't even see an asteroid from which they might have come. And there's hundreds of them, perhaps. There may have been many more, but we probably identify about 100 of these. Okay, so how are we going to find out about these mysterious missing planets? Well, it's relatively these are pretty clever, in that there are some meteorites, and they're the ones that we've been studying, particularly in at Birkbeck and in the Natural History Museum, which represent the surface of asteroids. They represent what's called the regolith. Now this is the regolith, the surface of asteroid Eros, okay, just before the Near-Shoemaker probe hit the surface. So you can see But, okay, there is no scale, but there are things that look big and lots of things that look little, and that's indeed what we're dealing with. We're dealing with a variety of rocks that are, some of which are large, some of which are much smaller, and if we were doing this on Earth, we'd probably call this a breccia. And if you take a piece of one of these regolith meteorites and look at it carefully using an optical microscope, as we can do generally with thin sections of meteorites, what you discover is that you find some bits that are very big, and this would be several millimetres across, and then lots of bits here that are very small. You can see that there is actually a boundary between the one bit and the little bits. And we can go much further than this. We can say that this piece, for example, because it's got so many fine little pieces in it, we know that that has experienced shock. It's experienced metamorphism, basically. Have you ever broken a window or seen a window break? How it breaks into thousands, especially if it's tough and glass things. It breaks into thousands of little pieces. Well, that's what happens with meteorites like this, which have been shocked by impact. Only they're doing it in 3 dimensions, so you've got thousands and thousands of pieces in all directions. Okay, so what's this going to tell us? Well, if an airless body with its surface of regolith sits around in the solar system for long enough, things are going to fall onto it. Meteorites are going to fall onto it. And that's exactly what we see in this diagram. Now, this is tricky because instead of showing you what the meteorite looks like in thin section, this is an electron, a backscattered electron image of the meteorite. You don't really need to know what that means, except that we can make these images very nicely in Birkbeck with our electron microprobe. But the important thing to know is that the colour, the shade of grey if you like, represents something to do with the composition of the piece of rock or the mineral. And even without knowing anything else about this, you can see that this piece here has a much lighter overall shade of grey than all the bits here except for 1 or 2 sulfide minerals. And this indeed turns out to be a fragment of an impacting meteorite. It's a meteorite inside a meteorite. And the question then is, can these fragments tell us anything about the lost planets? Because they might come from a planetary body that we've never seen before. Well, this is an assortment of those rocks. As you can see, that's the one we just saw, but there's plenty of others. Some of them are down as small as 2 or 3 crystals, but some of them are quite large, and you can make quite a lot out of them if you know what you're looking at in the backscatter electron image. And then you can take, this is work that was done by an undergraduate student, I should say, about 2 or 3 years ago. And she used the electron microprobe to analyse all these different minerals in there. Let's go back. And depending on the colour is a different kind of mineral. And she was able to determine from this that this is actually a fragment of a known type of meteorite. This is a fragment of something called an archondrite. But she could only determine that by using the electron probe. This is a similar sort of thing where we find a fragment of what's known as a chondrite meteorite here. And we're going to hear a lot about fragments in meteorites from Natasha later on. And the reason we know this is a fragment of a chondrite meteorite is it's actually got a thing called chondrule in it. So this is a very much more primitive type of meteorite inside a brecciated meteorite. And just from using the electron probe again, we can determine what kind of meteorite it is. And then something we can't yet do at Birkbeck, I suppose we could always ask the Dean if he's got £500,000 to invest. I'm lucky, yes. We can actually analyse the oxygen isotopes of a meteorite or even a fragment of a meteorite, even a tiny little piece. And that's what's happened here. We've got two kinds of oxygen isotope ratios. I won't go into all the details, but there's a thing called the 18 to 16 oxygen and the 17 to 16 oxygen isotopes. And we can actually find fragments of material that are completely unknown, kind of like things that we have in our collections, but not exactly what we have in our collections. So it's quite easy to find pieces of missing planets that way. Oh dear. Ooh. I am in trouble, I'm sorry. Okay, it won't do anything now, so I can carry on. In a certain brecciated meteorite from Antarctica, and unfortunately we don't have to go to Antarctica to collect it, but there are people who do go, and they have collected, I was going to say hundreds of thousands, but tens of thousands of meteorites in Antarctica. And this is one that we happen to look at, and my colleague in Birkbeck, one of our chaps who looks after the electron probe and Beard, he wanted to have a look at something here that I had originally analysed by probe and I couldn't understand it. This is a very strange piece of rock. It looks like nothing in this backscatter electron image, but when we start putting colour onto our diagrams to show the abundance of different elements in the rock, we start to see a pattern here. This is the piece of rock. So this is the silica content, and in this case, the brighter the colour, the more silica. So these pink things here turn out to be a variety of SiO2 quartz, or something very similar to quartz. We also have potassium, sodium, calcium, and aluminium in these in our analyses here. And when we put this information all together, we can describe what minerals we're looking at. And it turns out that these pink ones here are indeed some kind of quartz mineral. And this thing here, it is some sort of feldspar. Let's see if the next diagram will come up with that. Okay. So, this is our interpretation. We call this a plagioclase feldspar phenocryst, which basically means it's a large crystal in an igneous rock. Here we have tridymite, which is the variety of quartz. Here we have albite. When we put all this together, I think even our first year students, certainly my second year students, will recognise this texture as being extremely similar to the texture we get in a thing called a granophyre, a porphyritic granophyre, from the Isle of Skye, where the first year students go on their field class. And as soon as we saw this, we realised that this was essentially a piece of granite, or granophyre. Now, granites don't occur very often in the solar system. Most of the granites that you're going to find occur on Earth. However, using oxygen isotope ratios again, we discovered that this is kind of a fingerprint. This is where our granite plots. The Earth would plot over here, and the rocks, the meteorites in which they're found, plot in a completely different place. So this tells us that the granite, the microgranite, is not from the parent asteroid that the rest of the material in the meteorite is from, and it's not from Earth either. Now, something I didn't mention in my first go round the mineralogy of this rock. Am I going backwards? Yes. But something I didn't mention was the one phase that we really had difficulty in identifying, and that's this phase here in pale blue. I say phase because it's not a mineral. It turns out it's glass, and it's glass with immensely high sulfur and chlorine. When I say immensely high, 11% of SO3 and 0.5% of chlorine. Now, there is no planet in the solar system that has sulfur and chlorine on it, except for Mars, of course, and shown that it probably doesn't come from Mars. So we've probably got another lost planet here. And then finally, we also found some other material, in this case a banded opal. Now you're going to say opal, isn't that the stuff that you make chains out of? Yes, but in this case it's been found in a meteorite that has no other kind of volatile phase in it at all. And we think, we're not absolutely sure how the opal has been formed. It's all this banded stuff in here. And we think that this may represent interaction with a water-rich or an ice-rich meteorite coming in and landing on the surface of our asteroid. We can't prove it completely because of our oxygen isotope ratios again. Unfortunately, opal is a structure that tends to, it's very open, it interacts with its environment, and unfortunately the opal from this point here, which is more like our host meteorite, has interacted with terrestrial water in the Antarctic. So unfortunately we can't quite prove that, but we are pretty sure that the opal is in fact extraterrestrial. And again, we don't find opal in very many places in the solar system, other than on Earth, but we're pretty sure this is not Earth opal. I think it's probably from interaction of a icy planet, icy planetesimal that came in and impacted on the surface of our planet that we, sort of the asteroid from which this material has all been collected. Right, so before it disappears, before it disappears, summary, we have fragmentary evidence that there was in existence before the current solar system planets were all finished and accreted and made. We have evidence that there were previous generations of planetesimals and small planets that were destroyed in the early solar system. The evidence includes astronomical observations, it includes the ungrouped meteorites that I've mentioned, all these clasts that I've mentioned in our asteroidal regolith breccias, which collect meteorites naturally. Some of the fragments that we find are actually easily related to a known pair of bodies, in other words, some sort of known asteroid. But many of them may be from these previously unknown and unsampled lost planets. Thank you very much.
Questions from Hilary?
Yeah. What would you consider as where to look next for some very solid evidence that you could say there absolutely was another planet?
Where would I look? Well, I'd certainly look through as many pieces of brecciated meteorite as I could. The problem is that if they're out there, they're not lost. If they're yes. Yeah. So we're looking for evidence of material that one of the things that might be interesting to do is to, when Pete's busy roving around on Mars, he might just look at a few meteorites on Mars, because they might be different. There are meteorites that have landed on the small, large asteroid, small planet Vesta. We know that there is material of meteorite origin that has landed on Vesta. So looking at those, looking at breccias from the moon, there's all sorts of things we could do.
Any more questions, or you're keen to get a drink?
We're keen to get a drink, aren't we?
Yeah. So there's a half-hour break before our final two talks, and there should be some drinks waiting outside, I hope. Do come back in about half an hour to our final two talks.
It's an absolute nightmare. let me stop. Shall we stop it?
Do you want to
yeah, you can hear the number. I mean, I've emailed them a lot.